Welcome back to Schrödinger's Chat, the podcast where I explore the real science behind the biggest questions in the universe, as well as some of the quirkier science we encounter every day. I'm Anna, a sixth form physics student with a lot of curiosity and a passion for understanding how the world works. From the smallest particles to the largest galaxies, join me as we unlock the mysteries and wonders of the universe and explore how physics shapes the world around us. Italian astrophysicist Margherita Hack said, "The stars are not very different from us. They are born, they grow old, they die." Now in this episode, we're going to find out just how closely we are linked to the stars, and maybe find out how we're related in a way you might not have even realised. We're going on a journey back to before Earth, before the solar system, all the way to the birth of the universe. So get comfortable and cast your mind to the cosmos. What are you made of? And no, I don't mean bones and muscles or even your cells. I mean, what elements make up your body? It turns out that about 99% of your body mass comes from just 6 elements: oxygen, carbon, hydrogen, nitrogen, calcium, and phosphorus. And then of the remaining 1%, most of it, around 0.85%, comes from 5 more elements, which are potassium, sulfur, sodium, chlorine, and magnesium. The rest are trace elements present in only tiny but still vital amounts. But where did those elements actually come from? How did the raw materials for life, or for you, first form? To find out, we'll have to trace our origins all the way back to the very beginning of the universe, the Big Bang. In those first few moments after the Big Bang, the universe was unimaginably hot and dense. As it expanded and cooled, the first elements were formed, mostly hydrogen with some helium and tiny traces of lithium. These were the simplest elements, just 1 or 2 protons and neutrons, and they made up the vast majority of the universe's matter. But that leaves us with a problem. The heavier elements, like the carbon in our cells or the calcium in our bones, weren't made in the Big Bang. So where did they come from? The answer lies in the stars. Okay, so now we've established that hydrogen and helium were the first elements created in the universe, we need to understand how stars forge the elements that we are made of. At the core of every star, there's a process happening called nuclear fusion. Inside a star, gravity compresses the core until temperatures soar to millions of degrees. Under these extreme conditions, nuclear fusion begins, the process that powers stars and creates the elements. So, in a star like our Sun, the dominant fusion process is the proton-proton chain. Here, in the Sun's 15 million degrees Celsius core, individual hydrogen nuclei, or protons, are moving so fast that when they collide, they overcome their electrostatic repulsion, which is present because they both have a positive charge, so they repel each other. But they are moving at such high speeds that they can overcome this repulsion and they fuse together. In a series of steps, 2 protons combine to form deuterium, which is hydrogen with 1 proton and 1 neutron in the nucleus. Then a proton collides with this deuterium to form helium-3. 2 helium-3 nuclei then merge to produce helium-4. And a small amount of the mass involved is converted into energy, and this released energy is what we see as light and heat, which fuels the warmth of our planet. In larger, more massive stars, the fusion process can follow a different pathway called the carbon-nitrogen-oxygen cycle, or the CNO cycle. In this process, carbon, nitrogen and oxygen nuclei act as catalysts to transform hydrogen into helium at an accelerated rate. The CNO cycle dominates in stars that are significantly heavier than the Sun, where the temperatures are much higher and make this route more efficient. But fusion doesn't just stop with creating helium. When stars start to run low on hydrogen in their cores, they begin to fuse helium into heavier elements through the triple alpha process. In this reaction, 3 helium nuclei, or alpha particles, combine to form carbon, and under even higher temperatures, carbon can then fuse with helium to produce oxygen. These reactions gradually build up the periodic table element by element. Now already you can begin to see how the size of a star influences the fusion process, so let's take a quick detour to just look at the evolution of stars. So all stars begin their lives in nebulae, giant clouds of dust and gas floating through space. And under the pull of gravity, this gas begins to clump together. As it collapses, gravitational potential energy is converted into kinetic energy, which in turn becomes thermal energy. So parts of the cloud heat up and grow denser. Eventually, this forms a protostar, a kind of star in progress, if you want. Once the temperature and pressure in the core become high enough, nuclear fusion kicks off. Hydrogen atoms begin to fuse into helium, releasing huge amounts of energy. The star now officially enters what's called the main sequence phase, the long, stable middle of a star's life. Our own sun is in this phase right now, and will be for billions of years more. Now, what happens next depends entirely on the star's mass. If the star is low or medium in mass, like our sun, which weighs about 2 times 10 to the 30 kilograms, and is a medium star, it eventually runs out of hydrogen to fuse. The core contracts and heats up, allowing helium fusion to begin, and the outer layers expand outwards. The star becomes a red giant, and yes, it really does glow red. Cooler stars appear redder, just like cooler flames. Over time, the star sheds its outer layers, leaving behind just a hot, dense core. This is a white dwarf, a stellar ember that just slowly cools over billions of years. Eventually, it fades into a black dwarf, which is actually just a theoretical end state that's so cold and so faint that it would be nearly impossible to detect. But if the star is much more massive, several times the mass of the Sun, its story is far more dramatic. After the main sequence, these stars swell into red supergiants. In their cores, fusion doesn't stop at helium. They're hot and dense enough to fuse heavier and heavier elements, carbon into neon, oxygen and magnesium, oxygen into silicon and sulfur, and silicon into iron. But then the fusion stops, because iron is kind of a dead end. Fusing iron doesn't release energy, it actually consumes it. So once the star's core is made of iron, the delicate balance between gravity and pressure collapses. In just seconds, the core implodes, and the result? A colossal explosion, a supernova. This is one of the most violent events in the universe, but it's also one of the most beautiful. Supernovae are where many of the heavier elements in the universe are forged: gold, platinum, uranium, all born in that final moment of a star's life. What's left behind depends again on the star's original mass. A very massive star may collapse into a neutron star, a tiny, ultra-dense object made mostly of neutrons, where a single teaspoon would weigh billions of tons, which is almost incomprehensible, I think. Or, if the original star was even more massive, gravity wins completely, and the core collapses into a black hole, which is a point of infinite density from which not even light can escape its gravity. This entire sequence, the slow fusion in small stars to the rapid fiery reactions in massive stars, demonstrates how a star's mass determines its evolution and the elements it produces. It's this life cycle that ultimately creates a diverse array of elements present in our bodies and on Earth. But how did these elements go from being scattered across space to being in us? Well, following the supernova explosion, the heavy elements synthesized in the star's core are violently expelled into the surrounding interstellar medium. This enriched material, which contains things like iron, silicon, carbon, oxygen, and many other, mixes with nebulae. Over millions of years, regions within these nebulae experience gravitational collapse, forming dense clumps that will eventually become new stars. Now, if you remember, these are the protostars that we talked about earlier. Surrounding these newborn stars are what's called protoplanetary disks, and they are flattened, rotating structures made of gas and dust. Within these disks, solid particles collide and come together to form one mass through a process called accretion, and this gradually builds up into planetesimals, which are just sort of building blocks of planets, and ultimately full-size planets are formed. Closer to the protostar, the temperatures are higher, favouring the formation of rocky planets, which are composed largely of elements with high melting points like iron, magnesium, silicon, and calcium. Earth is one of these planets, formed from this material that once belonged to ancient stars. The iron core of the Earth, for example, originates directly from the stellar nucleosynthesis processes, just like the calcium in our bones and the phosphorus fundamental to DNA. Even volatile compounds, such as water, likely arrived during the later stages of Earth's formation. Many scientists believe that icy comets and asteroids formed in the colder outer regions of the early solar system and delivered significant amounts of water and organic molecules to the Earth. Intriguingly, the hydrogen atoms in water molecules can be traced back to the hydrogen from the Big Bang, connecting the entire chain of cosmic evolution from the birth of the universe to life emerging on Earth. Okay, so now we know that the elements we're made of come from stars, and we know how these elements show up on Earth. But how do these simple atoms turn into something as amazing as a living creature? This is where the chemistry of life gets really cool. Most of life's chemistry is built around just a handful of elements: carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. Remember how we talked about these being forged inside stars? Well, carbon is especially important because it's great at making lots of different kinds of bonds, which means it can build all sorts of complex and stable molecules. Now, there are four main types of big molecules that make up living things. First, there are carbohydrates. These are sugars and starches that provide energy and structure. Then there are lipids, which are fats and oils, and they help build the membranes that hold cells together and store energy. Next, we have proteins, which are made up of smaller pieces called amino acids. Proteins do almost everything inside our bodies. They help reactions happen, give cells their shape, and act as messengers or workers. And then finally, there are nucleic acids, like DNA and RNA, which are the instruction manuals for life, carrying the genetic information that tells our cells what to do. Phosphorus is key here too, because it's part of DNA and molecules that store energy, like ATP. And sulfur helps give proteins their shape and strength. What's incredible is that these elements and molecules all work together in such an organised way that life can grow, reproduce, and even think. So when you look at yourself, you're really a walking, talking collection of ancient star remnants assembled in such a specific and intricate way that it's possible for you to be alive, which is really cool. I think it's pretty mind-blowing to think that the atoms making up your body have travelled across space and time, been part of ancient stars, and now come together to create you. Every breath you take, and every cell in your body, every thought and action, is underpinned by atoms and molecules that originated in ancient stars billions of years ago before life even existed. So life is really the universe's way of organising matter into incredibly complex and astonishingly self-aware systems. Okay, before we wrap up, let's take a moment to just zoom out again, zoom way, way out, and think about the incredible timescales involved in this whole story of Stardust. So, the universe itself is about 13.8 billion years old. Right after the Big Bang, the universe was an extremely hot, dense plasma of particles. Then within minutes, the first simple atoms, mostly hydrogen and helium, formed as the universe cooled down enough for protons and neutrons to combine. But it wasn't until roughly 100 to 200 million years later that the first stars even began to form. These first stars, called population 3 stars, were massive, short-lived, and made almost entirely of hydrogen and helium. Because of their size, they burned bright and fast, living just a few million years before exploding into supernovae, scattering the cosmos with the first heavy elements like carbon, oxygen, and iron. These stars really invented live fast, die young. From these stellar explosions, clouds of gas and dust enriched with heavier elements slowly came together over hundreds of millions to billions of years, eventually forming new generations of stars like our Sun and planets including Earth. Our Sun formed about 4.6 billion years ago, from a cloud enriched by many previous generations of stars. The Earth formed shortly after, and even then it took tens of millions of years for it to cool down enough and develop the conditions needed for life. So, when you think about it, the atoms in your body have been travelling through space and time for billions of years, from the nuclear furnaces of ancient stars, through supernova explosions, through clouds of cosmic dust, and finally into the building blocks of our planet and ourselves. This incredible journey across time and space connects us really closely to the cosmos, and I think it's a reminder that we're not just observers of the universe, we're participants. made from the same ancient material that's been around since nearly the beginning of time. So, as we've seen, the Earth is a complex, dynamic product of billions of years of cosmic recycling, stellar birth, life, death, and a continuous transformation of matter. This intricate cycle creates the diverse chemical elements and environments necessary for life to exist. So, when we say that we are made of stardust, it's not just a poetic metaphor, believe it or not. It's a precise scientific truth that deeply reflects the connection between ourselves, our planet, and the whole universe. And I think there's something quietly powerful in that. We're not actually separate from the cosmos, we're made of it. The very blood that flows through our veins carries a history within us. I think astrophysicist Carl Sagan put it best. He said, "The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself." And I think that is the really cool thing, this idea of the universe acknowledging itself through what it creates. Similarly, Brian Cox said, "We are the cosmos made conscious, and life is the means by which the universe understands itself." That's all for now. I hope you've enjoyed this episode. If you have, be sure to leave a review or a comment, and go check out Schrödinger's Chat podcast on Instagram, where I post all sorts, from extra facts relating to the episodes to clues to the next episode, and all sorts of other fun physics and science content. If you have any feedback or questions, please send an email to schrödingerschatpodcast@outlook.com. The link to do this is also on my Instagram, so definitely go and check that out. Thank you so much for listening. I'll catch you in the next episode, but until next time, stay curious and remember, you are a star. Pretty much. Bye!